Hi, everyone. Microphone. Check, check. So, it's been a year, and we're seeing each other once again at the PhD Positive Hack Days Fest. So, I'm happy to see you all. So, the title of my presentation actually has a lot of meanings. The small composition that we heard at the beginning, and it's really original, was performed by Joe Perry in 1994. I'm not Joe Perry, I'm just Georgi Alexandri, lead development of the statistical analysis of source code from Positive Technologies. My today's presentation is the third one in a series of presentations related to the exponential growth of data in symbol analysis. So what are we going to talk about today? You know, after the first presentation of this series, we were talking about a special case where the growth of data is much lower than exponential. In the second presentation of the series, we are talking about how to use different heuristic approach in order to cut corners, to use all sorts of approximations to reduce the size of memory and to mitigate this exponential. After these two presentations, quite an interesting feedback came. People said that these are quite exciting topics, but on the other hand, the formulae used in the presentations make the perception of the material more difficult. And on the other hand, they play the role of a certain step in these developments. So let me bring these things together. Let's first talk about general things related to symbol analysis, and then discuss that exponential problem using the formulae that we have already got used to. So let me remind you what symbol analysis is all about. But for this, you need to recall the idea of abstract interpretation. It's some transformation of the source code into some other presentations to research the properties of this code. All this said, the interpretation of code is not happening. Symbol analysis, an explicit interpretation of code is not happening. Symbol analysis is based on three tenets. That symbolic execution. The second one is that all the data, the parameters of inputs calls to this outside systems are mentioned by symbol analysis as unknown data, the symbols that can take any admissible values unless there are some constraints imposed on them. And the third tenet is that symbol analysis operates with all the possible branching waves in the process of execution of the source code because it meets the unknown symbols. And if someone wants, then using these links, you can understand the definition in deeper and a more formal way. This said, symbol analysis is not a new way. People started talking about it at the end of the 80s when the first works appeared saying that symbolic analysis can be used to generate test scenarios in application development. And then at the end of the millennium, some work in the neighboring areas started appearing where researchers started discussing if there are other mechanisms that can be used in symbolic analysis. The renaissance of the symbolic analysis happened in the middle of the first decades of the 21st century, when all sorts of implementations appeared. Some of them are shown on the slide. that I have selected following my own internal feeling. And now we can say that we're at a stage when hybrid approaches in the implementation of symbolic analysis appeared. So from all the simple attempts are made to take things from other areas into symbolic analysis in order to get problems solved. A certain mathematical data model is used in symbolic analysis, which is called the symbolic virtual machine. It's IMC. Now, any mention of DMC, Devil May Cry, is absolutely circumstantial and was never thought of by the scientists who developed this. Okay, it's a joke. So the first element here is the current instruction in the source code being analyzed. The second letter is about the memory of the virtual machine with registers, variables, memory areas, and so on. And the third component is the current condition that you get, or feasibility condition that you get in the symbolic analysis. Quite often it contains the unknown symbols. I'm sorry, the clipper doesn't work. And if you got interested in how exactly the translation of instructions is happening in symbolic analysis, what kind of data is used in symbolic analysis, and also what's happening under the hood, then you have an excellent opportunity in exactly a month from now to visit the great city of St. Petersburg and listen to the presentation about that. And you get more information about this following this QR code. Okay, that's the end of my PR speech. All right, in our symbolic VM, we have this condition. And researchers, when they started to design all these series in the 1980s, already asked the question. So we have a VM, just a regular VM, and it has a specific feasibility condition. It has some value. But what to do with a symbolic virtual machine where this condition contains some unknown symbols? And in a general case, it's not clear how to interpret them compared to a usual VM. Just like it always happens in mathematics and computer science, we got help from the neighboring areas, exactly from the Boolean satisfiability problem and the satisfiability modular theory. There are local variables, brackets, and all sorts of logical operations there. As an example, you can use a statement of the form A or B. And in the satisfiability analysis, we're talking in terms of a logical formula that can be applied in a certain theory. It could be a theory of substantial numbers or regular numbers or others. For instance, example conditions A is more than 5 or less than 100. In this case, as a theory, we have a linear theory on integers. In this sense, SMT is even older than symbolic analysis. And as of today, we can say that there's implicit organization and the official standard at the same time, SMT lib, satisfiability modular theories library, that says how you can formulate these things so that SMT solvers could get some solution. So to understand if the solution is feasible or it is false from the outset. So I'm showing some tools here that allow doing that. Let's take a look at a simple example of an SMT request to understand what's happening there. In the first operations, certain SMT options are being set. Then we set the theory based on which we're working. In this case, we say that our theory is a linear logic over integers. Then we declare variables. And then we get the main block setting the constraints, the feasibility of which or impossibility of which, inachievability of which we want to check. In this case, we have two linear equations of this form, x times 2y equals 20, or x times y times 2. So we check solvability, and as you see here, it is. And in the last command, we get the specific value. In this example, we see that we need to take x equal to 8 and y equal to 6 to get the solution. This is how SMP looks currently. We got a bit digressed. Let's come back to symbolic analysis and take a look at this on this example, what conceptually it is. We have a small function that accepts three parameters. In the body of functions, we have a declaration of three local variables, x, y, and z. And in the management branches, we add some values depending on the input parameters. And at the end, we return the concatenation of the three variables. At the moment of concatenation, there are two admissible values for each variable, and the concatenation in sum generates 8 admissible values, because for every local variable we can take one of two admissible values and combine it with the rest of the admissible values. And had we had n variables rather than 3, and if every variable had k different values, we would have got, omitting some parameters that we have considered in the previous presentations, we'll get that the rate of growth of admissible values is exponential. And this is a fundamental problem of symbolic analysis, that it has an exponential growth rate. If it is more pleasant for some to hear it this way, you could say that symbolic analysis has an exponential number of branching options. It's a so-called path explosion problem, and in a certain sense, nothing can be done about that in a general case, and we're trying to fight this in some specific cases. So at this note, I congratulate you on getting through the first part. And now we are about to embark on the second part, where we'll try to get this problem solved another time. In order to speak the same language, we need to recall certain terms. Variant is a pair, y and x, where x is a certain value and y is a certain feasibility condition. The variative set is the set of all the variants of the expression. Let's now see how expressions are built in symbolic analysis. Imagine we have a certain expression G and it has sub in expressions. Because of symbolic analysis, these expressions can be variative with their variants and values. These conditions and values can also be expressions with sub-expressions. And we get to a recurrent definition of what an expression is. This is an expression with sub-expressions, where each of these expressions is a variative set, which has conditions that are also expressions. And it goes all the way until all the expressions contain variative sets. So in order to get a specific value of expression G, we need to fix some variant, take its value, recursively get its admissible value, and then take a condition or constraint for this value and get the variable, the admissible value for it. But let's take a look at the schematic. We'll understand that for one's admissible value in the fixed value of the variant, we have an entire set of admissible values as conditions of this admissible variant. In other words, the number of admissible variants is growing much faster by conditions rather than by values. And here we get a lawful question. Okay, how can we fight these conditions? How we can reduce the number to mitigate the growth speed? Before fighting the problems, let's take a closer look at our enemy. We have a small example, accepting a number of parameters. In the body of this function, there's a branching construct. So let's take a look. Quite often, the conditions for this construct is a set of conjunction and disjunction that contain expressions based on these theories. Of course, there can be some negations there, but for the most part, this is a set of conjunctions and disjunctions. This is about the way they look. And now you have a question. Okay, they look about like this, but how can we store this in a program's memory in symbolic analysis to work with them? Here we'll make a step aside and recall and maybe recognize, if you haven't known that an abstract syntactic tree is an oriented tree, the nodes of which are operators and the leaves are operands. And once again, for this logical expression, we get this abstract tree, semantic tree. Recalling you that an abstract semantic tree does not have parentheses, does have brackets. So take a look at this tree. Actually, it's one of the variants of storing a condition in the memory of a program. Let's write it down in a more formal way. What do we have? We have a certain binary tree that can be of two types. It's either a leaf, where the node is some expression that we get, or it's a non-terminal node, which has a type of operation, conjunction or disjunctions, and also possibly it has left and right subtrees. But what advantages and drawbacks this variant has? Firstly, is the compactness of storage. We use a limited amount of memory to store this information. Second, the determinated character for the same formula will always be getting one and the same abstract, and in this case, binary tree digression. This will be enforced if we have a determined grammar. Unless if we don't have it this way, we'll make it be that way. And so we'll also have an obvious thing. We'll have the recurrence of code. All the operands will be repeated in going through this binary tree from left to right. But unfortunately, the big drawback is that the speed of search in the binary tree is extremely low. In the worst case, when we have a case like this, we have a linear search speed, and unfortunately, it makes our life really hard. So let's now go from a binary tree to the binary search tree. So for this, we reshape our tree. Firstly, we add a key to the leaf, and this key will be related to our expression. And then we, in non-terminal nodes, remove the operation type and carry it out of our binary search tree. And instead of it, we'll add some expression that we'll be looking for. Then, because we get expression in non-terminal nodes, we'll also add a number key for which we may run a search. Therefore, we've done two things. We've said that this binary search tree contains operands specifically for a specific type of operation, conjunction or disjunction, and so that we have added the number key of a search related to the expression as part of this tree. In these keys, we want to implement one simple axiom. For two equal expressions, this key should be the same. So what's the key for these? So what are the properties of this tree? Of course, it's still compact in terms of storage. But as to deterministic character and repeatability of the code, it completely depends on how this number key is calculated. The search speed has grown a bit, but we're still a special case when this speed can be linear. Okay, the binary search tree is not a very good fit. Let's try self-balancing search trees. These are the trees that automatically maintain the height minimally possible with certain operations, insert or deletion operation. 1 second, and now you see some kinds and representatives of this family. And another digression. Today we'll have a lot of lyrical digressions, so once in a while I've decided to speak. So for instance, black and white trees, up until a certain point in time, they were used in the cause of operating systems of the Linux families to build virtual address space in the processor and virtual ranges as part of it. The B tree families are used for indexing of the databases. AVL trees are used in the organization of certain unchangeable data structures. That was a digression, but actually all these trees can be split into large groups by one criteria. Those that are balanced in height and those that do not guarantee the height balancing. So the trees of that group tell us that their height will never exceed a certain logarithmic value. In terms of red and white trees, red and black trees, it's an algorithm of 2 elements. In case of AVL trees, is 2.5 of the number of elements, and L3 is a logarithm on the base of k. Of the number of elements. The second group also tries to balance the height, but it doesn't guarantee that the height will be lower than a certain logarithmic value. And in certain cases, this will lead you to a linear height. So there's a probability of such cases to happen. So we'll try to operate with self-balancing trees balanced in height. Let's just, for simplicity's sake, call them balanced trees. This slide shows different advantages of the approach. Having closed our eyes, we can say that they're compact in storage while we're closing the eyes, because the guarantee of logarithmic height does not come for free. You need a certain number of bytes, information bytes, to achieve that height. In different trees, it can be calculated, but nevertheless, the determinability and repeatability is also depends on the case, but the speed of search speed has grown. As alternative, we could take a look at the hash table, where for each expression following a certain hash function, a certain value, hash value will be calculated to become a key in the table. What are the advantages of this option? Again, closing our eyes and putting our hands on the heart, so we can say that the compactness of storage and the search speed are quite good. They will depend on how good the distribution is for the hash function that we've selected, and also on how collision problems will be solved based on open addresses or on lists, or how we implement that. As to the deterministic character and repeatability will depend on the hash function that we've selected. Okay, so we have been reviewing all these different options. So why are we selecting a structure that should provide for a fast search? Actually, for this, we want as early as possible to reduce the conditions and to understand if the solution is achievable even before we start the analysis. Okay, can we use anything else? The next element that we can use are polyadic operators. These are operators that has an arbitrary number of operators. They're also multi-R, n dimension, and others. But we'll be using the term polyadic operators, and we'll make the following horse move or knight move. I will take a condition, in this case a conjunction and conjuncts, so it has n minus one conjunctions, and we transform it into just one conjunction, which will include n operands, and then we'll be working with conditions like that. They said, of course, we'll have to adapt our data structure for this process, but because this is just a small wrapper for the sake of convenience, and we won't dwell on that. Okay, what else are we going to use? In actual fact, we can use the property of a mathematical model. It's Boolean algebra. We're not going to get into what Boolean algebra is. Algebra is, what advantages it offers, but if somebody's interested, Boolean address is a distributed mesh, and we can discuss that. But here, we are interested in very simple things. What properties this Boolean algebra has, this data structure, and how we can use them. So this slide shows these property, and let's take a look what they can give us. The idempotentiality. It tells us that if we have some operator with repeated events, we can throw them out. This says that in our data structures, we can remove all the repeated elements that will save the memory and boost the search speed. Then this thing says that we can work with the supreme says that if we have a conjunction of several operands and conjunct it with several true expressions, we'll always be getting a true expression because there doesn't exist a false expression for that. In the first case, it was the adjunction, and the same for conjunction with negation. We'll always be getting a false expression. The immersion says that again we can improve the search speed. Supremum and infimum tell us that in a variative set we can fix one option and throw out all the rest. So in symbolic analysis, we fix one execution path and throw out all others, which reduces the total number of time of work and of operation, immutability, and also sociability. Sociability, together with some polyadic operators, gives us a small bonus. Having some operand and applying a certain operation, like conjunction with conjunction, we can take a current polyadic operator and add a new operand as part of it, because our polyadic operator can take any number of operands, and nothing stands in the way for us to expand it. And now the distribution capability. It says that we can open up the parentheses to get some presentation. This is the only property that doesn't offer us any advantages either in memory or in speed. It can just be used. This is about all. Oh no, I see the exclamation mark. I understood that we forgot Boolean algebra property that relates to the operation of negation. Let's take a look at them. Involution, double negation, we can remove that and just bring the memory down a little bit. The additivity is states that we'll always be getting a true expression in this case. This is one of the properties that allows us fixing one variant in the entire variable set and considerably grow the speed of search. And De Morgan laws allow us changing the order and sign of operations. This is the property, just as distribution property, that does not offer us any gain in the speed of memory, but it allows us operating. I hope the developers are here in this room, and we as developers quite often write a lot of code that has constraints or conditions. Even when we send calls to the database, requests to the database, it quite often happens that compilers and databases don't often work very well with optimizing these conditions. And if we try if we recall these properties, we may make the life of compilers a little bit better. Okay, coming back. So we've talked about the properties, we have databases, we have the operators, we're trying to bring these all things together. But this whole data structure starts standing in the way. We chose a data structure so that it should be about the search of the element that we need. But Boolean properties also require a fact to check if the negation is also present. And as a result, we get situation that in order to apply Boolean properties, we need to run two searches instead of one. Okay. Of course, we would like to optimize this somehow. What can be done as one of the options? It doesn't make any difference what kind of data structure we're dealing with. It's what the important fact is that the search is run on a certain number value. So let's be imputed enough to add a certain variant. So these values for the expression itself and its negation should be the same. So we'll make our distribution a little bit worse, but what will it give us? Instead of an operation equal to two searches, we'll just run one search operation with the return of values from the data structure and compare it with the expression that we're looking for and with the negation of this expression, and we'll get the number of operations equal to a single search, and maybe a two operation of comparison that would be considerably lower than two search operations. Okay. Clicker. Okay, we've run through a lot of things, and then you have a question. Is that all? Can we just wrap up and leave? Actually, no. After all, our transformations, the conditions have a very different look, and we need to take a look. We have normal forms: conjunction normal form and disjunction normal form. Conjunction normal form is some conjunction where each operand doesn't contain any other conjunctions, other disjunctions or negations. And same thing for disjunction normal form. There's a theorem saying that any logical expression can be reduced to a normal form. Well, unfortunately, we're not going to prove this theorem right now because the time of the presentation is very limited. Instead of this, we can look at what steps we can make. So as we reduce the logical expression to a normal form. If we take a look at the properties, these are just the properties of Boolean algebra that we have discussed. And for your understanding, let's take this logical expression and reduce it to a conjunction normal form. First, we apply the De Morgan form, then we apply other properties to get the normal form. This is the normal form with which it is convenient to work, and more than that, all the solvers I mentioned in the beginning of our presentation work with this. And here you may arrive at the most important question that's printed. And Georgi, why have we done that? If there are SMT solvers, we can just take a condition, put it into an SMT solver, and get fun from life. The answer is, as always, very simple, and it's reduced to one symbol. Oh, optimization. Let's take a look at the mouse. telltale example. Okay, click it on fail me. CVC5 1.2. On the left, you have the large parameters of this SMT solver. And in the center, you see the expression. So under these conditions, this expression doesn't offer a solution after dozens of minutes. After that, I just stopped waiting. Let's take a look closer. At the end, we have some terminal operator that does the following. If the integer equals 0, please return 0. Otherwise, return the value of dividing 0 by this variable. So it always returns 0. And if you explicitly put it into this expression, turns out that there's an expression, the solution, and it finds the solution in just a few seconds. So if you explicitly set this condition, it will solve very well. Another example, have a system of 5 equations and 4 variables, four unknowns. SMT can't solve this problem in dozens of minutes. And the solution is within the range between 5 and 20, I think. Okay, what can we do? So we have another represent, Z3 4.14. So FMT can't solve it for dozens of minutes. And in a couple of hours, I wasn't able to get an answer from it. Okay, CVC5 in 3 hours. Okay, YC2, 6.5. Which quite often gets prize places in S&T contest. It also can't solve it in dozens of minutes. And the first solution, because we have more module here, is in the range of about 100,000. Then you have this question, so there are S&T systems, and so why can't they solve? Why is it all so bad? Actually, the answer is extremely simple. SMT belongs to the NP-hard class of problems. So in the general case, in order to understand whether the solution exists, so whether the statement is derivable, you require the time not less than exponential. And as a result, you get a situation that symbolic analysis has the exponential growth rate. SMT is exponent, that exponent, absolute and acceptable. So one way or the other, simplifying conditions either for SMT or for compilers or for databases is required in order to make the life of our colleagues a little bit better. And so we are gradually wrapping up. So what has stayed outside? We haven't considered the algorithm of solvability that are used in SMT solvers. We haven't considered the Perel, SRL. We haven't considered local stochastic algorithm. We haven't covered the Howard's logic or triplet that's used for verification of certain conditions in software. It's often used in the derivability analysis. We haven't used the BDD and all kinds of its modification, the simplified binary diagram, multi-terminal binary diagram, and so on and so forth. And of course, we've only considered basic normal phones. We didn't consider all the variations, but I hope you understand that the time of presentation is limited and you can't fit everything into one presentation. So therefore, it's just a presentation of a whole series. The third installment in the series. So you can use this QR code to come to the presentation, leave your comments, and also to understand how the organization of our track is happening. With this, I would like to thank you for being with us, and I'm prepared to answer your questions. Georgi, thank you very much for this presentation. And apart from us calling on everyone to use the microphones to ask questions, I would like to remind you that leaving feedback for the presentation, you get an opportunity of winning the book of incredible Lovelace and Babbage.
Меня слышно, да? Замечательно.
So we get the question. You can hear me. My name is Konstantin.
В том числе формальной верификации по работе.
I'm also into formal verification by way of my work. In all these solvers, I have found one trait. You never know. And even in your presentation, you said, and I got tired of waiting and press Control C. You know, some problems are solved immediately, and in some cases, you have to press Control C. Sometimes after a couple of days of waiting. Your best practice. What's your best practice? How do you decide how long you're morally prepared to wait? That's a good question. Put it this way. We use different SMT solvers. This includes a moment when we used our own custom SMT solvers that met the declaration. And so we have a very simple policy for the limitation. This is limitation in terms of the size of memory, number of operations that they can apply, and also one on the time of operation. I won't be able to give you an exact number. It's under NDA, but the time is quite low because we work with a lot of expressions in symbolic analysis, much lower than the one I mentioned. I hope that I managed to clarify the situation for you.
Кажется, вопрос не закончился.
I think we run out of questions. And Konstantin, again, I left the microphone too early. So, yes. But look, then you will probably have been very upset because having waited another moment, maybe you could achieve that. Unfortunately, there are situations where you have waited for 100 minutes and then in minute 101 it would have solved. But by the number of the variables, you can't always realistically predict how long the SMT solver will take. If you indicate a specific theory based on which the work is done, the SMT solver may start working faster. If the logic is not known, in these cases, you have to expand the class of theories being used. And in this case, SMT will have to enumerate a larger number of variants. So unfortunately, that's just a fact of life. Dear friends, I'm still calling on you to ask questions. We're awarding a book for the best question among those who are with us in this room. So far, we just have one leader. Your chances are high. Hello, my name is Alexander. I'm also interested in SMT solvers. As far as I understand, in your product, you used some prior optimization in order to feed the results of this optimization to SMT solvers. Why don't you add some open source optimization into the SMT solver to share your work with the public? It's a good question. Actually, two answers. Answer number one, quite often SMT solver try to apply these optimizations because one way or the other they work either in the normal form or with different binary solvability diagrams. But unfortunately, they don't apply all of them because they have less information about the field. So the field is known in analysis much better than SMT. That's one reason. The second reason why we use this, you have to take all the optimizations, put them as part of the solver, wait until it's solved, until it's accepted, and because most SMT solvers develop in certain universities that are located in certain countries, I'll be quite cautious saying that you may run into some problems. And quite often we report some cases in the use of SMT solvers that certain cases don't really work. Or if they had worked okay in the previous version, under this version, everything is broken. So these are the two answers. I hope I'm making you happy, Alexander. Hello, my name is Fedor. I have a question. What's the space for using heuristics in SMT solvers? Oh, it's a good question. I'm not going to get into details because the topic for a separate presentation. Maybe I'll do that in the future. But one or the other, in SMT solvers, solutions based on enumerations are solved. It's typical algorithms, Dorfman, Kuppen, Divanov, if I remember this family, and these stochastic algorithms. This is an algorithm that fixes some value of the value, the true or false, and based on that tries to use different reduction procedure to derive some expression. If we get that, everything's fine, we get the expression, but if not, here all the differences start. We need to change some solution based on the current result. And here we're getting into the area of science where scientists try to understand what kind of approaches can be used. For instance, statistical algorithm, the return happens as a DSL algorithm. Conflict is defined based on our choice and based on the type of conflict. The replacement of single space disjunctions is happening with subsequent verification. In stochastic algorithm, randomization is applied based on the current result, and putting it bluntly, some transformation is used. So the solution is transformed into a number-based function. So in a general case, it looks about like this. Hello, my name is Maxim. I have one comment and one question. A comment to what one of the previous colleagues said, how long we're prepared to wait. This is basically a stop problem. Alan Turing formulated it. It's solvable. And a question. As I understand, solvers yield a specific, an accurate answer to the question with a 100% guarantee. What about the probability? Let me comment. Let me explain. This problem is solved in different ways in different projects. For instance, antivirus products need to give the answer in a very short time regarding whether the program is dangerous or not. For this, they enumerate all the branches of code. They do it fast, but do it without the guarantee. What's your opinion on that? A good question. I'll say a couple of phrases. Phrase number one. It's fuzzy logic. It's an area of science of dealing with what needs to be done when you don't have a clear understanding of the situation. What's the specific situation in our case? Everything is absolutely simple. We apply these approaches in certain cases because we can't guarantee that it's a solution, but the solution of a system, one way or the other, is needed for the user to validate the understanding whether they have vulnerabilities or not. And this way, you can just mark that they have a certain probability of a hit without a certain guarantee. Thank you. Then the second part of the question. How about making two-phase analysis? Phase one would be look for the probability. I think you understand what I mean. A good question. A simple answer. Well, to a certain extent, we have this. Dear friends, we'll be able to take one more question if you have it. I'm actually a bit struck. I would like to dispel one of the wrong statements by the previous person. It's not a deterministic question, deterministic thing. It's a Turing computable problem. Okay, let me correct everyone. It's an NP full complete problem with it's solved in some polynomial time. There's a class of NP hard problems that are solved over the time not less than exponential. SMT solvers belong to NP hard problems. So what we're talking about here is that we're trying to understand there's some source code we're analyzing. Are we going to complete it analysis or not? The thing is that all the different constructs are feasible. Not only Alan Turing, but there's also Rice Ethereum saying that without, well, it's a separate topic of a presentation. I'm not going to open the cards. So without any additional actions, we won't be able to understand whether it will stop in a general case or not. So to be as formal as possible, these things look alike, but stay somewhere on the side. So, any more questions? I'm prepared to take them. Okay, I think that we've run out of questions, which means that it's about the right time of choosing the one who gets the book from the Peter publishing. Just one? One. A good question. Actually, I am divided either toward to Peter or to the person who asked about what we do with SMT probabilities. I would let it be Peter's question about the solvability algorithms. Peter, come to us and we'll hand you your gift. Georgi, thank you very much for your presentation, dear friends. Please don't forget to leave your feedback for this presentation. Okay, thank you for having joined us, and I wish you all the good time at the Positive Hack Days Festival. And so we're going to have a very, very short break of about 5 minutes, and we'll continue talking about optimizations. Please stay with us.